It is the loneliest size in space, 99% the diameter of Earth, and yet this small rocky world sits in the dark with almost no air around it, like a candle that burned through its own jar. The James Webb Telescope just looked straight at it and found an empty sky. And what it found in that empty sky is rewriting what we thought we knew about how planets breathe. If you have ever wondered what happens when a telescope designed for the first stars of the universe turns around and points at the closest possible alien Earth, this is the place to be. Subscribe and ride along, because every week we sit with one quiet, real science story, told slowly, in plain words, no shouting, no hype, just the sky being honest. Let us pull back a little so a complete beginner can be caught up. For almost all of human history, the only planets we ever knew were the ones sharing our sun. Mercury, Venus, Mars, Jupiter, Saturn, and a few others. We mapped them. We sent robots to a few. We learned their weather and their gravity and their colors. But in the back of every curious mind, there was one dream. Are there other suns out there with their own families of worlds? The first big hint that the answer was yes came in 1992, when two astronomers named Alexander Wolszczan and Dale Frail announced the very first confirmed planets ever found beyond our solar system. Those first worlds circled a dead star called a pulsar, a star that had already exploded and collapsed into a tiny dense beacon. They were almost certainly not friendly to life. But the discovery cracked a stubborn door open. It proved once and for all that planets are common, not rare. The universe was busy making worlds, far more often than we had dared to hope. A few years later, in 1995, two Swiss astronomers named Michel Mayor and Didier Queloz found the first planet around a sun-like star, 51 Pegasi b, a giant ball of gas the size of Jupiter that swung around its parent star in just 4 days. That discovery was so important that it won them the Nobel Prize in Physics in 2019. And it made every astronomer start to wonder whether quieter, smaller, rockier worlds might be hiding right next to the loud giants we were spotting so easily. Then came the real breakthrough. In 2009, NASA launched the Kepler Space Telescope. Kepler did not take pretty pictures. It did something quieter and far more patient. It stared at one small patch of the night sky in the constellation Cygnus, and it counted the faint flickers of starlight coming from more than 100,000 faraway stars. Every time a planet passed in front of its parent star, Kepler saw a tiny drop in brightness, just a sip of starlight blocked for a few hours. By timing those sips, Kepler could measure how big the alien planet was and how long its year was. For almost 10 straight years, Kepler watched. By the time Kepler ran out of fuel in 2018, it had officially confirmed 2,626 planets beyond our solar system and had flagged roughly 2,000 more candidates waiting to be confirmed. Suddenly, the night sky had gone from a handful of planets to thousands of them inside a single human lifetime. Among those thousands were the first rocky worlds, small planets the size of Earth or a little bigger, and many of them sat in what astronomers now call the habitable zone. That is the not too hot, not too cold region around a star where liquid water could in theory sit calmly on the surface, the same kind of region our own home planet lives in. Now here is the part that makes this moment in time feel almost historic. The one telescope built to test those hopeful planets is called the James Webb Space Telescope, or JWST for short. Webb did not launch until Christmas Day 2021 after more than 20 years of planning. It is the most expensive science instrument ever flown, costing roughly $10 billion. It carries a gold-coated mirror 6.5 meters across, which is more than twice as wide as the old Hubble mirror, folded up tight for launch and unfolded once in deep space. And it does something Hubble could never do well. It sees the universe in infrared light, the kind of light we feel as warmth on our skin. That matters a lot. When starlight filters through a planet's atmosphere, the different gases down there leave fingerprints in the infrared colors. Webb can read those fingerprints from worlds dozens of light years away, like listening to a guitar string vibrate from across a football stadium. So, in late 2022 and early 2023, when Webb finally turned its golden mirrors toward the small rocky planets we had been cataloging for years, the entire astronomy community leaned forward. The very first confirmed Earth-sized planet Webb studied was LHS 475b. It sits about 41 light-years from Earth in the constellation Octans. Its diameter is 99% of Earth, a near-perfect twin in size. It is rocky, not a gas ball, and it zips around its parent star once every 2 Earth days. One year, there is just 1/48th of a single Earth year. The team behind the discovery, led by Kevin Stevenson at the Space Telescope Science Institute in Baltimore, hoped to see a thick atmosphere with greenhouse gases, the kind that could keep the surface warm and maybe even wet. What Webb actually saw was almost the opposite. The atmospheric signal was flat. There were no clear signs of methane, carbon dioxide, or any heavy clouds. In plain words, the planet appeared to be a bare rock drifting through space with no significant protective blanket around it. Pretty surprising because the scientists had prepared for almost any outcome except that one. Let me stop here for just a second because I want to hear from you. Did you already expect that a planet the exact same size as Earth would turn out to be a bare rock, or did the news surprise you when you first heard it? Drop a quick reaction in the comments because this is the kind of question your gut answer tells you something real about how you picture the universe. So here was the first lesson of the Webb era of rocky planet science. A planet that looks like Earth in size can act nothing like Earth in nature. That small, mostly silent result reset the optimism of the entire field in a single published paper, and this was only the very beginning of what was coming. The next planet Webb looked at made the surprise even bigger. Beyond LHS 475b sits a star system that astronomers had pinned their highest hopes on. It is called TRAPPIST-1, named after a small ground-based robot telescope in Belgium that first spotted it back in 2016. TRAPPIST-1 is a tiny red dwarf star, only about 9% the size of our Sun, sitting about 40 light-years from Earth in the constellation Aquarius. Around it, in tight, close orbits, are 7 rocky planets, all about the size of Earth. 3 of them sit inside the habitable zone of the star, where temperatures might allow liquid water on the rocky surface. The TRAPPIST-1 system has been, for years, the closest thing we have to a real family of Earth-like worlds, the first place where you could imagine walking onto alien ground at sunset. Then Webb turned toward the innermost planet, TRAPPIST-1b, a world the size of Earth that circles its star once every 1.5 days. The team, led by Sebastian Ziebe at the Max Planck Institute in Germany, published their results in 2023, and the message was harsh. Webb saw no thick carbon dioxide atmosphere on TRAPPIST-1b. If the planet had a heavy blanket of carbon dioxide like Venus, the readings would have lit up like a beacon. They did not. The readings were flat, matching a bare rock or at most a paper-thin atmosphere. Then came TRAPPIST-1c, the next planet out, in the same year, 2023, with the same kind of result. A separate team found no dense carbon dioxide atmosphere on C either. Now this is the key point. Carbon dioxide is one of the easiest gases for Webb to detect in infrared light. If it were there in thick amounts, Webb would not miss it. So both B and C appear to be exposed, bare worlds, more like Mercury than Venus, more like gleaming stone than warm oasis. Why does that matter so much? Because red dwarf stars like TRAPPIST-1 are not gentle parents. They flicker and flare, they bathe their close-in planets in bursts of harsh radiation. If a planet does not have a thick atmosphere to protect its surface, that surface gets blasted by every storm the star throws at it. So the dreams of warm, rainy oceans on TRAPPIST-1b or C got a serious reality check. And this was happening live with real data in front of the entire astronomical community. Then in 2024, Webb pointed at TRAPPIST-1d, the third planet in the system, slightly farther out. The hope had been for a thicker atmosphere, perhaps a more Earth-like one, rich in nitrogen or water vapor. Instead, the first published Webb results ruled out a clear Earth-like atmosphere on D2. The verdict was softer than on B and C, because D's signal is harder to separate from the noise of its star, but the writing on the wall was the same. The inner family of TRAPPIST-1 does not seem to be wearing much air. I want to pause here with one quick question, because it connects this whole rocky planet story to you. If our most hopeful Earth-sized system turns out to be mostly bare rock, what does that say about the odds of finding a real Earth twin out there somewhere? Are we rare in the universe, or just hard to find? Drop your honest take in the comments, single sentence or a paragraph, I will read every one. Meanwhile, in another part of the same star map, Webb was studying a strange, hot, almost angry little world called 55 Cancri E. This one sits 41 light-years from Earth, a little bigger than our planet, near 2 times Earth's width. Its year is the shortest known for any rocky world, just 18 hours. It circles a star like our Sun, just a touch warmer, so close that its day side reaches about 2,400 degrees Celsius, hot enough to melt almost every rock we know about. Imagine a planet practically hugging its star, glowing red on the side that faces its Sun, and even the night side is far hotter than any oven on Earth. In 2024, the team led by Renyu Hu at NASA's Jet Propulsion Laboratory in California used Webb to look at 55 Cancri E during 4 separate eclipses, when the planet slipped behind its star from our point of view. They measured the heat coming off the planet. The readings showed a drop in heat that hinted at an atmosphere. Specifically, the data suggested gases like carbon monoxide and carbon dioxide, the kind of gases that come out of molten rock when it simmers. The leading idea is that 55 Cancri E has a permanent ocean of glowing magma on its day side, and that ocean is outgassing, releasing vapor that rises into a thin, hot atmospheric skin, not thick enough to call a true sky, but real enough to count. Picture that for a moment. A planet very close to Earth's size where the ground is melted stone, and above that melted stone is a thin veil of smelly, hot gases. This is not the world of romance and storybooks. This is a world of fire and chemistry, and yet it teaches us something crucial. Even on a baked, tortured planet, an atmosphere can survive. Air does not automatically get stripped away by heat alone. Some worlds keep a little, even when everything around them says they should not. I have one quick curiosity question for you here, because this part is the part most people miss. If you were sitting on a spacecraft above 55 Cancri E, would you rather study the dayside lava ocean up close, or would you rather trace the thin chemical veil of gases above it for any sign of a story? Tell me which side of the planet you would point your instruments at, and why. The comments are open and waiting. Here's where the story takes a sharp turn toward hope, because Webb did not just deliver disappointment. Webb also delivered the first clear sign that a rocky planet in the habitable zone really can hold on to its atmosphere. Let me introduce you to a planet called LHS 1140b. It sits about 49 light-years from Earth, circling a small red dwarf star in the constellation Cetus. LHS 1140b is about 1.5 times the width of Earth and roughly 6 times more massive, a true super-Earth. Its year is 24 days long, almost matching the comfortable rhythm of Earth, which made it an instant favorite for habitability studies. The team behind this discovery, working with Webb in late 2024, looked for helium, a light-safe gas that is easy for infrared telescopes to spot when it floats high in a planet's atmosphere. They caught it. Specifically, they caught helium in the act of escaping from the planet, streaming out into space like steam from a kettle. That single detection tells us something enormous. There is enough atmosphere above the surface of LHS 1140b to feed that escape. The planet is not bare. It has a real blanket of gas, even if we do not yet know its full recipe. Even more intriguing, follow-up work in 2025 found that the helium signal had changed. The amount of escaping gas went up and down over time. That suggests the atmosphere is alive in the dynamic sense, responding to the activity of its star, puffing up when the star flares and settling back when it calms. The most likely explanation right now is that the star itself has become slightly more active, the way our own sun grows more restless near its 11-year sunspot peak, and that extra energy puffed up the planet's upper atmosphere, giving the helium a stronger push. Maybe the atmosphere has water, maybe it has nitrogen, we do not know yet, but we now have proof that the gas envelope is there and that it is not static. LHS 1140b is becoming the template for what a small habitable zone planet can look like when it still wears its air. This single set of measurements may be the most important result for rocky planets in Webb's early years. It shifts the question from, do atmospheres exist on these tiny worlds, to what kind of atmospheres exist and which ones breathe in the right way for life to join the party. That is a quieter, slower, far more powerful kind of progress than a single dramatic headline would ever suggest. Now let me take a breath and walk you toward the planet that has made the loudest headlines for very good reason. It is called K218b, sitting about 124 light-years from Earth in the constellation Leo. K218b is 2.5 times the size of Earth and 8.5 times more massive, so it sits in a category called sub-Neptune, bigger than our world, but still small enough to dream about. It circles a red dwarf star every 33 days. In 2023, a team led by Niku Madhusudhan at the University of Cambridge used Webb to scan the atmosphere of K218b in detail. The result was published in a major scientific journal, and it lit up every screen in astronomy. They found clear evidence of methane, a gas made of carbon and hydrogen, along with carbon dioxide. They also found a tantalizing but weak signal of dimethyl sulfide, or DMS, a molecule that on Earth is made almost entirely by living things, mostly by tiny ocean plankton. The signal was right at the edge of what Webb can detect, so scientists are being extremely careful not to call it life. They are calling it a question. But oh, what a question. The most exciting part is that K218b sits inside the habitable zone of its star. The surface temperature could allow liquid water to exist under its hydrogen-rich atmosphere, and Madhusudhan's team proposed a new category for this kind of world, the Hycean world, half ocean, half sky, a planet with deep global oceans and a thick hydrogen envelope above. Nobody has seen those oceans directly, but the gas mix is consistent with that picture. Let me ask you the big question right here, because it is the one every person who watches a story like this secretly carries in their head. If Webb's faint signal of dimethyl sulfide on K218b turns out to be real, what would that discovery do to your day-to-day life? Would you carry the news around like a small, quiet secret, or would you tell the first stranger you meet? Drop one sentence in the comments telling me what you would actually do. I want to see how a discovery like this lands inside real people, not just inside a lab. While Webb kept scanning, another team chased a quieter, more subtle signal on a world called GJ486b. This one sits 26 light-years from Earth, circling a small red dwarf in the constellation Virgo. GJ486b is about 30% larger than Earth and 3 times its mass, a rocky super-Earth. Its year is 1.5 days, so it sits very close to its small, cool star. In 2023, a team led by Sarah Moran published data showing that Webb had picked up clear water vapor-related signals around GJ486b. The first reaction in the press was optimism. Water vapor on a small, rocky world. But the honest second reaction was caution. Cool star spots on the star itself can also produce water vapor signals that leak into the planet's data, so we still cannot say for sure whether the water sits in the planet's atmosphere or whether we are seeing the star's face. This is exactly the kind of honest science we want. Scientists openly admitting what they do not yet know and designing the next observation to settle it. That kind of mature attitude is what makes the field trustworthy in the long run, and it is also why you should keep watching these stories instead of believing only the loud headlines. So when you put the whole Webb scoreboard side by side, here is what you get. LHS 475b is mostly bare stone. TRAPPIST-1b, C, and D are bare rocks with no clear, thick atmosphere of the kind we can easily measure. 55 Cancri E has a thin, hostile atmosphere of volcanic gases above a magma ocean. GJ486b shows a possible water vapor signal we cannot yet pin to the planet. LHS 1140b has a real, breathing atmosphere with helium leaking off it. And K218b has methane, carbon dioxide, and a faint hint of dimethyl sulfide that might, just might, be the chemical signature of life. This is the early scoreboard, all from a single telescope in less than 4 years of work. Nothing has settled the great question yet. But the scoreboard has changed shape almost every time Webb swings its mirror in a new direction. And the very last finding, that hint of dimethyl sulfide on K218b, hits a nerve in everyone who hears it. Because if it is real, then the universe is not just making worlds, it is making worlds that cook up chemistry that life on Earth also cooks up. Now here's the part where I want to step back from the data for a moment and connect all of this back to you and me sitting here tonight. Webb has now studied about a dozen small rocky worlds in or near the habitable zone, and the early scoreboard looks nothing like the optimistic cartoons many of us grew up with. Some of these places are bare rocks with no protective gas envelope, some are burned into lava oceans, some carry thin, smoky, strange atmospheres, some show hints of real water, some show chemistry that might, just might, whisper of biology. And that is only the beginning. Roughly 70% of the small rocky worlds Webb is set to study are still ahead of us on the schedule, queued up, waiting their turn in the mirror. And here is the deepest lesson in all of this. Earth is rarer than we hoped in some ways and more common in others. The conditions that made Earth friendly, abundant liquid water, a balanced atmosphere, the right distance from the right star, are not guaranteed just because a planet is the right size in the right zone. They are usual only when a long list of small, perfect things line up, like chemistry, magnetic field, plate tectonics, water delivery history, atmospheric escape balance, and on and on. Webb is now showing us, in plain words, how rare or how common each of those ingredients actually is. So when you look up at the night sky tonight, the points of light you see are no longer just pretty lights. Some of them are stars with families around them. Some of those families include small rocky planets. Some of those small rocky planets still wear their atmospheres. And a few of those atmospheres now carry chemistry that we cannot fully explain without whispering the word life. We are not there yet. We are not at the proof moment. But we are closer than we have ever been. That is the most honest, most exciting, and most restrained thing I can say about where we stand as a species watching the sky. Before I close, let me share one more thought that keeps me awake at night in the best possible way. Every photon of starlight we have been talking about, the ones carrying Webb's data back from LHS 475b, from 55 Cancri E, from K218b, those photons have been traveling toward us for years, sometimes for decades. We are reading the sky as it was, not as it is right now. If someone out there is right now building their own telescope and pointing it back at us, they will not see today's Earth. They will see Earth's yesterday, and one day when our great-grandchildren point a future telescope at one of these worlds, they will see an older version of it, perhaps with its own biology just beginning to color the chemistry of its air, perhaps not. That is the slow, beautiful, humbling scale of what Webb has started for all of us. Now, here is where I would love your help shaping what comes next on this channel. Webb still has thousands of hours of observation time left in its mission, and the team that decides where to point it listens to public interest too. If you could pick the very next small rocky world to study with Webb, what would you choose, and what would you hope to find there? Drop your pick and your hope in the comments. The ideas that come from curious people watching from home are not silly. They are part of how science culture grows, and I genuinely want to read what you come up with. If this quiet, careful style of real science storytelling is what keeps you watching this channel, I would love it if you would do 4 small things before you go. First, please subscribe if you have not already, so the next story finds you without a hunt. Second, turn on notifications so you hear about a new discovery the moment we publish, not 3 days later when a friend tells you about it. Third, drop one final comment telling me which of these worlds you would book a one-way trip to first, the Lava World 55 Cancri A, the Bare Rock of TRAPPIST-1, the helium-rich LHS 1140b, or the Methane Sky K 218b. I will read every single pick. And fourth, share this video with one friend who would find the slow unraveling of a real mystery as exciting as you do. Because stories like this grow best when they reach people who actually want the long, patient version. Thanks so much for spending this quiet hour with me. Sleep well, keep looking up, and never stop asking what is really out there. We will catch the next strange sky together, one story at a time.